This is a display of a 1 kilohertz square wave on the Analog Discovery Spectrum Analyzer. I am displaying this because this particular application uses a technique called a fast Fourier transform. In other words, what it's doing is it is sampling data in the time domain, and then it is converting it using an algorithm called the FFT into the frequency domain. So this is 3 kilohertz, this is 5 kilohertz, 7, and so on. What it shows us is that a square wave contains odd harmonics. In other words, this is the kilohertz fundamental. This is 3 kilohertz, the third harmonic, the fifth harmonic, seventh, and so on. And the value, of course, of a fast Fourier transform is that it computes these frequency components quickly. In a previous video, I talked a little bit about complexity and algorithms. And in that, I used the fast Fourier transform as one of the examples of how, by looking carefully at the problem and trying to break it down into a simpler structure, that is, a less complex computational structure, you can achieve in very, very little time what would take you a long time if you were to use a brute force method. So I'd like to talk about that a little bit more. I'm not really going to be getting down into the details of the FFT. Rather, I'm going to be talking about what it is about this particular process that led to the advancement called fast Fourier transform. In a previous video on algorithms and complexity, I talked about this book as a source of information on the fast Fourier transform. Well, as it turns out, even before I had the opportunity to publish that particular video on YouTube, a student asked a question, if there was any systematic way that you could go about looking at this question of complexity in algorithms and so on. And of course, I talked about a book on computers and intractability and other things. But one of the things that I especially want to talk about in this video, which I hadn't intended to do a follow-on, but it's illustrated here if you notice, there is a Cooley and Tukey reference in this fast Fourier transform book, dated in 1965. Well, the reason that I point this out is if you look just a little bit further down, you find a reference to a 1942 article by Danielson, and I hope that I won't mispronounce this, Lanczos. It turns out that the fast Fourier transform was known, or at least the method for computing it was known, before Cooley and Tukey published their 1965 paper, that's the paper most people point to. And frankly, it was that work and some of the work that was done at E-Systems by the author of this book that formed the basis of my understanding of the fast Fourier transform. But what's interesting is that article by Danielson and Lanczos in 1942 talks about essentially the same thing. In fact, some people, myself included, think that their algorithm is superior to the fast Fourier transform. It's basically the same thing. So I'd like to talk a little bit about that, and in passing, simply note that even Danielson and Lanczos were not the first individuals to work on this. It turns out that one of the most famous mathematicians of all time, Gauss, worked on this in 1805 and published some results. So what is it that's going on here? Well, one of the problems is, if you look at the original work by Fourier on Fourier analysis, he defines the Fourier transform in terms of an exponential with 2 pi I divided by n, where n is the number of samples that you're working with, or the number of data points. And normally, the way you would compute the Fourier transform is by summing over all of those a matrix multiplied by a vector. Now, don't worry about the details. I'm just talking here about what you would call the classical approach, or what some people might call the brute force approach, which is to just look in the book, find the formula, and then compute that for each data point. The problem is that this computation is of the order of n squared. In other words, as the number of data points goes up, the amount of computation required goes up by the square of the number of data points. So with 3 data points, it's 9. With 4 data points, it's 16, and you get the idea. One of the things that Lanczos and Danielson did in their article, which by the way appears in the Journal of Franklin Institute in 1942, is they managed to reduce the computation down to order n log n. And this reduction from n squared to n log n is one of the most important areas for people working on algorithms to consider. If you can find a way to compute the same thing using n log n, you reduce the computational complexity enormously. So what was it that Danielson and Lanczos, and later Cooley and Tukey, realized? Well, it was that if you take data points, this is time, and this is the data, and I've shown 4 bits here, but it could be any number of bits. What you're really doing is you're sampling a waveform like this. So at time 0, it's 0. At time 1, I'm saying it's 8. At time 2, it's back to 0. At time 3, it's at -8, and so on. So that's shown in this table. Well, what Danielson and Lanczos, later Cooley and Tukey, noted was that this data can be separated into 2 groups. It can be separated into even and odd samples. Now, what I have shown over here is this is f sub k odd, this is f sub k even. So you group these and you group these. That has cut your computation problem in half, but has produced 2 computations that you now have to do. But the interesting thing is, this process is recursive. In other words, you can then split these into evens and odds, and these into evens and odds, and continue doing that until you're down to just one function. And that was the insight that Danielson and Lanczos first published in 1942. So how is that useful, given that we already have the FFT? Well, I have put together a list of some ways of looking at algorithmic complexity that have proved fruitful for others in the past, including myself. And one of the things is to recognize the common problems that occur when you're writing an algorithm. The first is, don't just use the brute force approach. An example of that is the Fourier transform. If you use the brute force approach, you get order n squared. If you use a more enlightened approach, you get a better and faster execution, in fact, order n log n. Another area that often happens is in the process, you lose data. Now, for example, when you sample, we know from the Nyquist theorem and so on that you're losing data. You can only sample at a certain rate, and from that you only retain a certain amount of data. Every time you sample, you lose data. You lose data in between the sample points. You can also have nonlinearities that cause the data to be lost. So a fairly precise point becomes fuzzy. Another thing is the use of estimation. Sometimes the use of estimation produces variations in the data that if it were not estimated, if you were really using the precise values, you would see things that we'll talk about a little later under symmetry. The same is true of measurement error. If you're not very precise in how you measure things. And finally is representation error. So for example, if you sample something with 8 bits, but then you represent it in 4 bits, you are giving away or throwing away a lot of data. Obviously, one of the things that Danielson and Lanczos realized was that if you examine the data carefully, it could be processed recursively. Also, something they noticed is that the data had a symmetry to it. Now, if you've ever worked with matrices, you know that often data has a symmetry about the diagonal. Sometimes by grouping data, you can get a symmetry, like we just saw in the FFT by grouping the evens and the odds. And sometimes you will find that there is symmetry in the bit patterns. In other words, a bit pattern in one direction is exactly the mirror of a bit pattern in the other direction, and we'll see that in just a second. So this is the process that Danielson and Lanczos used to split the function, that is this function here, from 0 to F7, we're just representing in 8 bits, or 8 functions, into the evens and the odds, and then you split the evens into evens and odds, and then you split those into evens and odds, and eventually you wind up with just a set of data bits that are single functions. The next thing that they did is they applied bit symmetry. What they realized was that if you swapped the function 0 with the next bit, and you did that all the way down in groups, and then you swapped these two with these two, and so on, what you wind up with at the bottom is the final Fourier transform. That is the individual elements of the Fourier transform, the frequency elements. These are the time elements. These are the frequency elements. In the case of 8 bits, you have to do 3, that is 2 to the n, swaps. Another thing they realized is if you use an even or a power of 2 set of samples, or if you don't have that, pad it till you do have, it makes this process easier, and you can see why. Because if you have a power of 2, then 2 to the n is how many swaps you have to do to get the fast Fourier transform. Let's take another look at how that can be done in memory. Here, well, I've managed to turn it upside down, is a yet further improvement that they made. This would be one way of doing it, where you have a matrix and then another matrix, and you swap this element, you copy the first element, you swap this element here, this element goes there, and so on. Or you can do that right in place. In other words, you don't need the second set of memory locations. So you cut down the total memory needed by simply swapping this into a temporary location Then you swap this one up into that location and then copy the temporary into here. By doing that, you wind up with a much, much faster and much less time-intensive processing routine. Now, in the course of this, I came across this FFT algorithm, or a C implementation, by a student at the University of Texas, Jonathan Valvano, that he published in 2008. It is basically an implementation of this technique. In other words, the Danielson-Lanczos algorithm. And as most of you know, the use of FFT is prevalent in a great many instruments today. It is one of the things that has made digital signal processing the success that it is. Now, there also was a lot of work in chips and other things, some of it by Texas Instruments. In fact, E-Systems and Texas Instruments worked together on a lot of this stuff back in the 80s, and I lost track of it after that, but I know it continued to improve and so on. But my whole point in doing this video is to say, if when you're doing an algorithm, if you will look a little bit at the places where people often spend unnecessary time computing things, you can often save yourself and your customers a lot of time. Now, one reason that this is of particular interest to me is that my PhD dissertation was in a very similar area. I was able to reduce an n-square computational problem in digital logic to an order n log n problem. And I did it by first eliminating the representation error, going from what was in effect a 5-value representation to a 9-value representation. And second, by taking advantage of a technique that had been invented by someone else, just as if Cooley and Tukey had first looked at the Danielson algorithm, it turns out they did their work and then they discovered the Danielson work. But at any rate, had they done so, it could have saved them a lot of time. In my case, I discovered some work by a professor at Stanford called Tarjan on graph theory that was applicable to the problem I was working on. So by combining a couple of things and by eliminating some of the representation error and a few other things, I was able to reduce the complexity of the problem I was working on from an n-square problem to an order n log n problem. We're not always that successful in doing this. Sometimes what we do is we simply reduce it from n squared to n to the 1.5 or something like that. It's still better than n squared. So I urge you to think about these sorts of things if you do algorithm development, particularly if the algorithm is going to be executed on some very large data sizes. And you'll discover that just as Cooley and Tukey did, basically the same work that Danielson and Lanczos did, you can reduce the order of your computation to something that is more tractable. Once again, I realize not very many people are going to be interested in this on YouTube. I'm going to put it on YouTube anyway, just so that it's generally available. But if you do have some comments or suggestions, please post them there. But I realize if only 20 people watch this, that's probably a large number. So I would like, though, to sort of wrap up with this video the issue of complexity in algorithms and move on to some other things. But in the meantime, I hope everyone has a nice day.